Hello everyone, I am Ajinkya Gore and in this video I am talking about LIDAR systems. So moving on, what is LIDAR? LIDAR stands for Light Detection and Ranging. It is a remote sensing technology with active components. It is very similar to radar technology, but instead of radio waves, it uses ultraviolet, infrared and light in the visible spectrum. It uses shorter wavelengths compared to radio waves, and so it's very useful in detecting smaller objects which radar couldn't detect. LiDAR is based on laser sensors for transmitting and receiving, and due to the fact that it does not require any passive components like sunlight, it can be fully regulated from the ground station. Going to the next slide. So why is to use LiDAR? LiDAR or 3D laser scanning was developed in the early 60s for submarine detection from the aircraft, and early models were used successfully in the early 70s. Nowadays, environmental research is hard to imagine without the use of remote sensing techniques like light detection and ranging. It is used for generating precise and directly georeferred spatial information. Laser produces a coherent light source. It is an active sensor, so it does not require any sunlight or anything and can be used either during the day or night. LiDAR is popularly used a technology to make high resolution maps. Uh, I will be using the simplified version of LiDAR system to explain the fundamental principle of it. It consists of three major components: laser, telescope, and data acquisition system. Laser transmit the signal towards some distinct object, here in the case atmospheric scatter, and the signal gets scattered and detected by the telescope. The distance of the distinct object can be measured by noting the time the signal takes for traversing the distance between the transmitter and the target. Uh, let's focus on the component of the LiDAR system. The most important component is laser. The laser can have frequency ranging from 50,000 to 200,000 Hz. Depending upon the use cases, various wavelengths are used. For example, infrared is used for meteorology, near infrared is used for terrestrial mapping, and the light in blue-green region is used for bathymetry. I will be talking about bathymetry in more details in the upcoming some slides. Uh, Next important component of LIDAR is a LIDAR transceiver. Basically, it is a combination of transmitter and receiver. The transmitter emits laser pulses and receiver captures laser energy that is scattered or reflected from the target. There is a scanner which consists of three components: the optomechanical scanner, the ranging unit, control processing unit. The speed at which images can be developed is affected by the speed at which it can be scanned into the system. A variety of scanning methods are available for different resolutions such as azimuth and elevation, dual axis scanner, dual oscillation plate mirrors, and polygonal mirrors. The type of optic determines the range and resolution that can be detected by a system. Moving on, positioning system are very important component. When a light detection and ranging sensor is mounted on an aeroplane, satellite, or automobiles, it is necessary to determine the absolute position of the orientation of the sensor to maintain usable data. Global Positioning System provides accurate geological information regarding the position of the sensor and inertial location. These are devices provide the method for translating sensor data into static point for use in the variety of systems. There is operator interaction which control interaction with the flight controllers in the case of UAVs. The captured data is stored into some data storage device which could be used to generate X, Y, and Z coordinates of the target relative to current position. All the processing needed to generate these coordinates is done by some onboard computer like Arduino or Raspberry Pi. In this computer, the light detection and ranging mechanism just collect elevation data along with the data of inertial measurement device and which is placed in the aircraft and a GPS unit. With the help of this system, the light detection and ranging sensor collect data points. The location of the data is recording along with the GPS sensor. Data is required to process and return the time for each pulse scattered back to sensor and calculate the variable distances from the sensor or changes in the land cover surfaces. After the survey, the data are downloaded and processed using specially designed computer software. The final output is accurate, geographically registered longitude, latitude, and elevation for every data point is calculated. The LIDAR mapping data are composed of elevation measurements of the surface and are attained through aerial topological surveys. The file format used to capture and store LiDAR data is simple text file. By using elevation point, data may be used to create detailed topological maps. With these data points, even they also allow to generation of digital elevation model of the ground surface. In this slide, I am going to explain the working principle of LiDAR system in case of airborne devices. The working principle of live detection and ranging system is really quite simple. A LiDAR sensor mounted on an aircraft or helicopter. It generates laser pulse train which sent to the surface target to measure the time and it takes to return to its source. The actual calculation for measuring how far a returning light photon has traveled to and from an object is calculated by multiplying the speed of light and the time of flight, and the result is divided by 2. Accurate distances are then calculated to the points on the ground and elevations can be determined along with the ground surface buildings, roads and vegetations can be recorded. These elevations are combined with digital aerial photography to produce a digital elevation model of the Earth. The laser instrument fires rapid pulses of light at a surface, some at up to 150,000 pulses per second. A sensor on the instrument measures the amount of time taken for each pulse to reflect back. Light moves at a constant well-known speed, so the LiDAR instrument can calculate the distance between itself and the target with a high accuracy. Like we can see in the picture, there are some houses and trees, and the aeroplane can detect the variation of the topology of the surface. By repeating this in quick progression, the instrument builds up a complex map of the surface it is measuring. Now, I'll be talking about some important applications of the LiDAR system. The first application that I'll be discussing about is bathymetry or measuring depth of water bodies. Most of the initial uses of LiDAR were for measuring water depth. Depending upon the clarity of the water, LiDAR can measure depths from 0.9 meter to 40 meter with a vertical accuracy of 15 centimeter and horizontal accuracy of 2.5 meter. As shown in the figure, a laser pulse is transmitted to the water surface where through Fresnel reflection, a portion of energy is returned to the airborne optical receiver, while the remainder of the pulse continues through the water column to the bottom and is subsequently reflected back to the receiver. The time elapsed between received surface and the bottom pulses allows determination of the water depth. The maximum depth penetration for a given laser system is obviously a function of water clarity and bottom reflection. Water turbidity plays a most significant role among those factors. It has been noted that water penetration is generally equal to 2 to 3 times of the Secchi depth. Furthermore, the bottom and surface signal should be clearly distinctive to compute the water depth. In the case of shallow depths, these signals overlap, making it impossible to determine the water depth due to the interference between them. Second application is the land surveying. Airborne LiDAR scanners can be used to create a digital terrain model or a digital elevation model. Data can be gathered using a drone, aeroplane, or helicopter depending on the size of surveyed area. A plane can normally acquire swaths of 3-4 kilometers wide in a single flyover. Drones are cheaper, safer, and faster for small terrain surveys where the real human beings can't reach due to very critical conditions. Forestry and precision agriculture. LiDAR and aerial photos can be used to identify farm areas that use costly fertilizers to increase productivity. It can also be used to precision forestry to identify specific forest area in order to increase productivity, reduce cost, and preserve the environment, and also to construct the topological maps of that part. Power line inspection. Detailed information on power line and distance between poles can be extracted from the point cloud. This enables surveyors to analyze the detailed structure of the power line corridor, including vegetation, roads, and houses, and to identify the potential risks which can cause various issues. And the last application that I'll be talking about is mining. It can be used in mining to measure ore extraction space. This is calculated by comparing surface data to previous scans. Drones are often used to survey mines because a faster and more economical option than surveying using aeroplanes. Terrestrial laser scanners and mobile mappers equipped with sensors are also used to survey mines. So this was all about the applications part, and that was my PPT. Thank you.